This is tutorial video 3, part 3, regarding the finite element analysis of plane stress structures. We're going to be looking at the solver and post-processor stages of the analysis of a glass plate connection. So we will run the analysis, retrieve the results, and most importantly we will compare these results with hand calculations to validate this. The steel plate glass connection has the geometry as shown here. So it has a plate thickness of 10 millimeters and diameter of 100 millimeters. We've given the material properties and the physical properties, and we created a finite element mesh, and the plate is subjected to a pressure on the right hand side of 200 kilonewtons per meter, which is a pressure of 20 megapascals, a total load of 60 kilonewtons on this side. So we've created a submodel, and we have defined the geometry, defined the material, defined the physical properties, and we have assigned all of this to the elements. We have applied boundary conditions and applied the load. So we're ready to run the analysis. So we go to run analysis. We have switched off these two load cases, so we're only going to run the live load pattern. We run the analysis, and if you go to display, show the form shape. This is the form shape, so we can obtain the value of the deformation at every point. And if we come to this point here at the end, we see that the total deformation, the horizontal displacement U1, is 0.16 millimeters. We can check this value with a hand calculation quite easily. So for example, we know that the total load applied on the end is 60 kilonewtons. The stress will be 60 kilonewtons, so 60,000 newtons, divided by the area, and the area is 300 millimeters width and 10 millimeters thickness. So the stress is 20 megapascals. The strain is the stress divided by the yaw modulus, which is 72,000 megapascals. So that's the strain, which is 2.7 10 to the minus 5, and the elongation will be the strain times the length. So for an element like this, you could easily assume that all of this region here is in pure tension. So if we assume that the strain along this area here is constant, and we take this area from the center of the circle to the end, that's 60 millimeters, the elongation will be 600. The elongation will be 600 millimeters times the strain. So we obtain an elongation of 0.16 millimeters, which is very similar to the one obtained in the SAP. So we can see that the model seems to give reasonable results. The other thing we need to check here is that the reaction forces is what we expected. So if we plot the reaction forces, we go to display, show forces at the joints. These are the reaction forces, and at the edges, for all this region, the reactions are in tension. The reason for this is that we're pulling from this end, and because of Poisson ratio, this area here will get shorted in this direction. So the connections here are pulling from it, so that's why it should be in tension, whereas after the opening these are in compression. Now if we look at the reaction forces at the circle, so we go to select, group, circle, and we view the selection only, we can see that the reactions have a horizontal component along the entire circle, and then it has basically the opening is being squashed at the top and bottom by the reactions. Okay, if we go to view, show all, we can see all the reactions. If we add all of the vertical reactions, they should add up to 0. because there's no basically vertical applied load into the system. If we add all the horizontal reactions, they all should add up to 60 kilonewtons, which is the load applied on this side. To check this, we can go to Display, Show Tables, and we can show different results in a tabulated form. For example, we can go to Structure Output, and we can show the base reactions. We can show it, for example, just for the live load. And this is the table, and as you can see, this is the base reactions. So for the X direction, you see that they add up to 60 kilonewtons. When you look in the Z direction, it's almost equal to 0, as we expected. So now we have checked the reactions, we have checked at the deformations, and we can look at some of the values for the stresses. So if we go to Display, Show Forces, Planes, and we show S11, this is the horizontal stresses. If you don't know what S11 stands for, go to the manual. If we plot the local axis red is the 1,1 local axis, so we're talking about the horizontal stresses. You can see around this region the stresses are almost uniform, and they are equal to 20 megapascals as we expected, and as we get close towards the opening they start increasing, so you're getting a peak values of around 35 megapascals, and if you go towards the edges they reduce down to maybe 12 megapascals. So if you make a cut around this section here and you calculate the integral of the stresses, it should give you 60 kilonewtons, but of course the distribution here follows a different pattern than here, so you have a peak value here, a lower value there, and almost constant distribution on this area. You can also plot the stresses in the vertical direction. You can also plot the shear stresses, which are also quite important, and you see a large concentration of shear stresses around these two areas. And also you can plot the von Mises values, which you might want to use if you want to check whether the material is highly stressed or not. This combines both axial normal stresses and shear stresses to obtain these values. So these are different ways of checking the stresses along the structure. By looking at the reactions and by looking at the deformations, we can see that the model seems to be correct.